Hello, everyone. Welcome to our NCE training courses. I'm Jenny from NovaStar, today's host. Our training will start soon, and the topic is Basic Knowledge of NovaStar Control System. To provide you a good training environment, we sincerely suggest you to keep your audio on mute mode during the whole session. Please scan the QR code or click the link at chat room to sign in. If you cannot click the link, please copy and paste it to your browser. Feel free to leave your questions that are related to today's topic on the chat room. We will reply you later on the Q&A session. If you have any other questions that are not about today's content, please feel free to send an email to nce@novastar.tech. Now, let's welcome Lei. He's today's trainer.
Thank you, Jenny. Hello, everyone. I'm Lei from NovaStar. Welcome to our NCE training. I'd like to start with a short introduction of NCE training to the guys who are not much familiar with us. The full name of NCE is NovaStar Certified Engineer. We have trained more than 3,000 individuals all over the world since it started in 2014. By giving multiple courses and valuable chances to embrace the LED control system, NCE courses enable you to operate and maintain the equipment independently. Because of the special situation, this year we hold the training online. We are hoping more techniques could get the knowledge and a certification even in the hard time. This term, we will have 7 courses and a final examination. You could get an online training certification if you sign in for 6 courses at least. And pass the final exam, I hope you guys can go to all courses to make a good scores. Okay, today we will spend 1 hour together. For the first course, we will talk about the basic knowledge of NovaStar control system. And we also have Q&A time after my presentation. In this class, you will learn about 3 parts. The first is system structure overview, how to calculate cabinets of each output. And also, the most important is the screen connection logic. As we know, NovaStar is a company that develops the LED control system. So the first thing we need to know is, what is the LED control system? I believe some of you may not be very clear about what makes up the LED cabinet, which you work with every day. So let's see the LED module first. LED module is the smallest unit in the LED cabinet. One cabinet is composed of multiple LED modules. Here is a photo of one module, the front side and the back side. And we can read lots of information from this module, such as manufacturer name, module size, pixel pitch, driver IC, and so on. As we know, there are different kinds of LED modules from different manufacturers. So here I divide them into 3 different types of LED module, like DIP, SMD, and COB. DIP was very common many years ago. It is a classic package method. DIP usually have big pixel pitch and mainly used for outdoor. SMD is the most common package method nowadays, no matter for outdoor or indoors, because it's the technology is very mature. COB is the latest technology. It could reach much smaller pixel pitch, like 0.7 millimeters, something like that. So it's kind of technology meet up with the request of future of LED industry. And let's see the last picture. This is a difference between the SMD and COB package. As you can see, the COB package doesn't have PPA foothold and the 10 solder anymore. So that's the main reason COB package can make much smaller pixel page. Okay, let's move on. After the LED module, now we need to create an LED cabinet. LED cabinet consists of several modules arranged according to a certain rulers. And there is a receiving card and a hub card inside the cabinet connect to LED module through flight cable. So basically, this is what's inside the LED cabinets. Normally, there's only one receiving card inside each cabinet, but the pixel page is becoming smaller. So the resolution of each cabinet becomes bigger. Sometimes one receiving card is not enough. In this case, one cabinet may have two receiving cards inside. But for NOR LCD software, we still regard it as one receiving card was regarded as one cabinet in NOR LCD. That means the cabinet with two receiving cards like this will be regarded as two cabinets in NOR LCD connection. Okay, as we just mentioned, LED cabinet is composed of many LED modules. Then the LED screen is composed of many LED cabinets in the same principle. So as the principle shows, for the LED screen, it consists of several cabinets like this. Now, we know how to set up the LED screen. If we want to show image on the screen, then we need to set up the control system, right? Here we can see the control computer is connected to the sending card through the USB cable and Ethernet cable. So the PC can send control command to the sending controller. And also the PC connect with the sending controller through HDMI, DP, and DVI. So the PC can provide the video source to the sending controller. And also the sending controller connect the LED screen video wall through the Ethernet cable from the multiple outputs. So the image information can be displayed on the LED screen because the sending controller uses the Ethernet cable send out the signal to the LED video wall. This is a basic structure of the entire LED control system: PC, sending card, Ethernet cable, LED control video wall, LED video wall. Well, mostly the source resolution is different with the screen resolution. Here we can see the video source is like 1366 by 768. And the screen resolution is 700 by 500. It's much, the source resolution is much bigger than the screen resolution. In this situation, the screen will displaying only part of the video source. We call this kind of displaying pixel-to-pixel display. In this situation, we only use the sending card. Give the video source to the sending card, then displaying on the screen while pixel-to-pixel display. A video processor, if you want to display all the content on the screen, a video processor or software scaling is necessary, which can scale image resolution to the specific resolution. For example, let's see this. After scaled the resolution of the image through the video processor, the image is fitting to your screen size. Then we can get a complete display of the entire image. But depending on the screen size, the ratio of the image may be changed. So you can see this structure. Video processor, we add extra video processor to scale the resolution from the video source. And then we scale the resolution to 700 by 500. So you can see the whole image is fitting into the screen. Now the system structure will be like this. The video source comes from the PC, goes to the video processor first. Then the video processor will deal with the video source before providing it to the sending card, such as scaling. We are talking about the resolution. Let's see the standard resolution. As we know, the pixel pitch is getting smaller. The screen resolution on the same physical size will be bigger. As you can see from this picture, these are the common standard resolution from Full HD to 4K. On the right side, the numbers here indicates that different resolution has different ratio. Okay, now let's move on to the loading capacity. The loading capacity determines how many cabinets you can connect it for one output port and how many controllers you need for the project. So here, we need to know what is loading capacity. And when we talk about the loading capacity, we don't care about the pixel pitch or the physical size of the screen. The total pixel number is what we need. So we only focus on the pixel level. When purchasing LED screen from manufacturer, we only know the physical size of the cabinet or module. So how do we get the cabinet resolution? I give you the example. The cabinet dimension is 500 millimeters by 500 millimeters. The pixel pitch is P3.91, which is very common for us. Let's see how we can get the cabinet pixel resolution. We know the pixel resolution is equal to pixel width by pixel height. And pixel width is equal to cabinet width divided by pixel pitch. And pixel height is equal to cabinet height divided by pixel pitch. So the pixel, after calculation, you can get the pixel resolution. For this example, I will calculate with you together. Give me 1 moment. I open my calculator. Okay, so cabinet dimension is 500 millimeters by 500 millimeters. So we counted 500 millimeters divided 3.91, which indicates the pixel pitch. And the result is 127.8. That means the pixel on the width is 128. And on the height is also 128 because it's also 500 millimeters on the height. Okay, that's how we get the pixel resolution from the physical size. This cabinet pixel resolution is 128 by 128. Here is a Control 300, which is a very basic controller in NovaStar. The loading capacity of each output, as we all know, is 650,000 pixels for each output. 300 has 2 outputs, so that's why the loading capacity for the 300 is 1.3 million pixels. Then, after we know how to get the pixel resolution, let's see how many cabinets can be loaded by one output port. I also give you an example. When your screen resolution is 182 by 182 pixels, And each output port loading capacity is 650,000 pixels. So we also have a formula. The cabinet number is equal to port capacity divided by cabinet resolution. Then the cabinet number, we can get the results is cabinet number. Okay, I will calculate with you together. Like 650. So 650,000 divided by the cabinet resolution, right? 192 divided by 192. The result is 17.632. Okay, that's the results. That's how we get the cabinet number. The cabinet number, we cannot get 18, right? We only can get the maximum cabinet's number is 17. So that's why we can get the results is around 17. Then we can get the results 17 cabinets can be connected for each output port. Okay, but I got a question. Have you considered why each output port can drive 650,000 pixels? How we get, how we get these numbers, 650,000? Actually, there is a formula I'm prepared for you. Let's see. As we all know, we are using Ethernet cable to do the output from a LED controller to LED video wall. So 1 gigabus is the bandwidth of the Ethernet cable. And 93.6% of the bandwidth is the normal usage rate. And here, the common input color depth is 8-bit. And the frame rate normally is 60 Hertz. So now, this formula, we can calculate the loading capacity. So the Ethernet bandwidth is equal to loading capacity multiply frame rate multiply the RGB bit depth. So now let's calculate together how to get the loading capacity. Okay, we know 1 gigabus is 10 to the power of 9. So sorry, 10 to the power of 9. Let's do it. We multiply the usage rate, multiply the 0.936. So we can get this number, and we divided 24, 3/8. And we divided by the frame rate, 60 Hertz. You can see the result is just 650,000 pixels. So that's how we get loading capacity for the each output for the each Ethernet cable. Okay, after I calculate the normal loading capacity in the normal situation, but sometimes, maybe in some countries, the customer use not 6 Hertz as a frame rate. They are using 50 Hertz. What about the loading capacity? Is there any difference? Is there any impact on the loading capacity? So because of the time limit, so I just give you the result. If we lower the frame rates, but we're still using the 8-bit color depths, and loading capacity will be higher. Does that make sense? So this is very easy understanding, right? You can calculate by yourself. We will find the loading capacity will become bigger. And also, if the color depth is 10 or 12 bits, it's 10 or 12 bits, like you are using HDR video source, because HDR video source is 10 bit normally. So at that time, you will, what happened to the loading capacity? Is there any difference? So the loading capacity will cut down by half, actually. Do you know the reason why it can be cut down? Why it cut down by half? So I'll give you the reason. It is because 1 byte is equal to a bit. When your color depth is more than a bit, it will occupy another byte. So we will calculate as 16 bit. So if you use 10 bit or 12 bit, that's same as 16 bit. That's why your capacity will be cut down by half. Okay, I guess you guys are already get it. So let's move on. This is a form shows different frame rates, and color depths will have different loading capacity. I just summarized the different frame rates here and different color depths here. So you will get the different loading capacity result. But I want you guys to know that our loading capacity for the each output actually is a little bit more than 650,000. So that means as long as your pixels is not beyond this number, it will be fine to load this kind of pixels. So 650,000 is just for you to easy understanding, for you to easy to calculate the loading capacity totally. Okay, let's move on. Now we know for each output port, the loading capacity is 650,000 pixels. So what about the 4 output port controllers? So if one output is 650,000, so 4 output, it should be 2.6 million pixels. Because it's just like multiply the 4 times, right? But the result is wrong. Loading capacity for 4 output controller is not 2.6 million pixels. It's 2.3 million pixels. 2.3 million pixels is the real capacity of these products. Why? Why I can't get all the loading capacity? Now I will give you the reason. All of our 4 output controllers are using single link DVI as input. These are the normal single link DVI resolutions. We see the maximum resolution of single link DVI is 1920 by 1200. It's just 2.3 million pixels. So because of the input source limitation, the loading capacity of the 4 output port controller is 2.3 million pixels. That's the reason why the loading capacity of 4 outputs is 2.3 million. But please pay attention. We also support 2 special resolution beyond 2.3 million. It's 2048 by 1152 and 2560 by 960. This is about the bandwidth of video signal. So the concept of bandwidth is very important in the video industry. If you need to build a LED screen, the maximum loading capacity of the control system depends on the lowest bandwidth of the video signal channels. This form shows you the common video signal we used and its bandwidth. Give you an example. HDMI 1.4, the resolution is 2560 by 1600. But HDMI 2.0 is real 4K resolution, is 3840 by 2160. The bandwidth is bigger than 1.4. The same principle as the DP 1.1 and DP 1.2. The DP 1.2 is the real 4K bandwidth resolution, 1496 by 2160. Except the loading capacity limitation, there are also limitations on the width and height for our controllers. The total loading capacity here is determined by the quantity of outputs and input resolution, just as I mentioned. Our controllers have its maximum width and maximum height as well. Of course, the resolution should under the maximum capacity. Like, you cannot do the pixels number over than the maximum width and maximum height. So sometimes this will directly affect what controllers you can choose for the screen. And as we all know, you cannot get the maximum width and the maximum height in the same time because they have a total loading capacity as a limitation, right? So we know how many cabinets can be connected. It is enough. Actually, no. Let's see a real case. I give you a real client case. We can see the screen resolution is 1920 by 1152, and each cabinet is 192 by 384, and 10 columns by 3 rows. Customer only have control 660, system running at 60 Hertz. So my question is, how we finish the screen connection or how we finish the cabling? So we get this all information. We can calculate how many cabinets can be driven by one Ethernet port. Like 6500000. This is the loading capacity for each output. So we can divide the cabinet's pixel resolution, right? Like divided by 192 by 384. The result is 8.8. That means each port can drive 8 cabinets, cannot drive 9 cabinets. So the maximum cabinets can be driven is 8. Okay, let's keep going. So I know 8 cabinets is the maximum cabinets can be driven for each cable. So here I connect 8 of them, 7 of them, and 8 of them, and 7 of them for the 4 cables on this M controller 660. It should be okay, right? But I sent to the hardware the NOA LCD software warning me that exceed the loading range. That means it's too much for the output. The pixel is overload. Actually, not only port 1 is overloaded, other ports are also overloaded. Okay, let's see why it's happened. I give you 2 pictures. On the left, we connect 9 cabinets. On the right, we connect 8 cabinets. 9 cabinets, the result is over the loading capacity, 650 thousandths. On the right, 8 cabinets is lower than the loading capacity, 650 thousandths. But when our system calculates the capacity, it should be a complete rectangular area, like the gray part. In this gray part, no matter you have 9 or 8 or 7 cabinets, the rectangular area is the same, so the pixel count is the same. So actually, you already just connect 8 of the cabinets, but actually the NOI LCD will regard it as you connect the 9 of them, because the NOI LCD system can calculate as a rectangular area. Okay, let's go back to the case. The client only have one control 660. Does it mean the control 660 cannot work? No worries. We can change another screen connection way, like this. Port 1 loads 8 cabinets in the first line. Port 2 loads 8 cabinets in the second line. And port 3 loads 8 cabinets in the third line. And port 4 loads 6 cabinets as a rectangular. Click send to hardware. Let's see what happened. The information has been successfully saved. That means we can make the cabling like this. So the final screen connection will be like this. When we get the result is the screen connection logic is when we calculate the capacity, it should be a complete rectangular area. Let me do a summary. Today, we have learned the smallest units of the LED screen, modules, the basic structure of the LED control system, and also we know how to calculate the loading capacity and the screen connection logic. All these are very useful information and knowledge in this industry. Hope all of you could get it. Okay, this is that's all the presentation for today. Thank you for your attention and thank you for watching. And please scan the QR code or click the link at Zoom message zone to fill up the feedback.